Today we will be covering the topics of distance and displacement, speed, which is constant and average, constant changing and average velocities, constant positive and negative acceleration, and we'll be wrapping up the lesson with solving problems using equations of motion where the acceleration is uniform. Let's go ahead and begin. So kinematics is the study of motion, and motion, everything moves, right? Everything, even those things that are at rest. So people walking, we know what that looks like. Molecules bouncing, the earth is spinning, books sitting on the table. Motion is easy to recognize. In physics, it is hard to describe as we get further along, and we describe an object's motion as being relative to something else. For example, we are this one little planet right here, and we're on a trajectory, an orbit around the sun. So we are moving. So when we're on Earth, we are moving. However, depending on where you are being observed from, the motion is observed differently. So let's say you are on Earth standing still, okay? And we know that we are moving at the speed of Earth, which is 107,000 kilometers per hour, relative to the sun. So if someone were looking at us from the direction of the sun, they were on the sun, if that was even possible, they'd be dead. But if they were looking at it relative to the sun, we would be moving 107,000 kilometers per hour. However, if you were on Earth, standing still on Earth, looking at yourself, relative to the Earth, your speed is 0. So as you can see, it can get a little confusing where the observation is coming from. So we do say relative to. So relative to where will change your answer. So just be aware of that, and we'll go in more details later. Now, with distance and displacement, distance is a scalar quantity. It is the actual path that was taken. There is no displacement involved when you're talking about distance. It is always positive. There is never less than the displacement. So your distance will never be less than the displacement. It will always be the same or more. Displacement, on the other hand, is the shortest distance from the initial or starting point to the final point. It is a vector quantity. It has direction. It can be either positive or negative. And it will either be less than or equal to the distance that was traveled. So for example, if we have a person that runs 1,000 meters one full time around the track, right? So if they run one full time around the track, they will have run 1,000 meters. Displacement is the distance between the start and the finish, which here the person has ended up in the same place they started. So the displacement would be 0. Another example is a boy here who is walking from point A and heading east at 3 kilometers, or supposed to be 3 meters, and then heads north 4 kilometers to reach point C, his house. So the distance here that the person walked was 3 meters and 4 meters. So they walked a total of 7 meters. However, the displacement, which is this part right here, the resultant, right? It is the Pythagorean theorem, which gives us 5 meters. So obviously, the displacement is 2 meters different from the amount or the distance that was actually traveled. Here is another example. A person walks east for 5 meters, then turns around and walks west for 10 meters. So your distance that was traveled is 15 meters, but its displacement is a negative 5 meters. And you know that the negative does not mean that the speed decreased. It means that the displacement is happening in the opposite direction to what was initially traveled. Okay, so if you were pointed east when you were walking, if you go west for 10, then that's just showing, the negative just shows that you're going further along in the negative direction, in the opposite direction than you first started out. Here is another example. So the distance and the actual path that is being traveled by this butterfly follows the same line. So the black and the red dotted line. This is the actual path and the distance traveled. However, the displacement is much shorter than what the distance traveled. So that's just another visual representation of the difference between distance and displacement. Now, the sign of displacement, velocity, and acceleration. So when they're given, when we are in a one-dimensional example. So there's only two possible directions that exist to make things more simplistic. So a positive quantity means that the direction is to the right. A negative quantity means the direction is to the left. And this is just in a one-dimensional example. And of course, things get much more complicated. But for now, this is good to know. Symbols to remember, and this is going to be located on your data booklet in physics. So S stands for displacement, and it is measured in the units meters. U is initial velocity or speed, measured in meters per seconds. Velocity, final velocity or speed, is V, and they are meters per second, or meters seconds to the -1. And notice that velocity and speed are the same symbol. Acceleration is denoted as A, and that has an ms -2, and time is in seconds, and that one is T. So some of these symbols might look a little different than what you might remember. There are different equations that are using different symbols, and these are the ones that we need to know. So start getting familiar with them. Speed. Speed is a scalar quantity. It is the rate of how fast an object covers distance in any given unit of time. Okay, so it is the change in the distance traveled, right? And it is the time that you traveled that distance. So for example, the cheetah runs 50 meters in 2 seconds. If you were to take the distance traveled, which was 50 meters, and divide that by 2 seconds, then we can say that over the course of the 2 seconds, each second that cheetah ran 25 meters. Velocity, denoted by the italics lowercase v, is a vector quantity that changes, that pretty much the definition is that it's a change in position or displacement in respect to the change in time. The equation is right here, and note that the s refers to displacement, not with the overall distance. So when you're using the same exact equation for solving two different things, it might just be best to define speed and velocity in words. However, when you're doing exams, then obviously you're just using the same equation. So just keep in mind that they might have different meanings, so you'll just have to remember the difference between velocity being displacement and speed being distance. So for example, 60 kilometers per hour, when there is no direction given, that is speed. This is an example of velocity because there is a direction given. Alongside with here, 30 meters per hour at north, 22.8 degrees east. That is a velocity because clearly that is a direction given of the magnitude. Now, when we're talking about speed and velocity, a car does not always move at the same speed for the entire trip. So there's this car here that the drive time is 31 minutes. So let's say for the first 7 minutes right here, he was traveling at 50 kilometers per hour and then stopped for 2 minutes. And so it had a 0 speed, and then it increased and then decreased over the course of 5 minutes, 10 minutes, and 7 minutes. So how can we communicate this information? So there's different ways. One way is to say what the average speed is of the object. So the average speed is pretty much just the total distance traveled over the total time. So if we traveled 60 kilometers per 1 hour, you can say our average speed was 60 kilometers per hour, which means that in the total of 1 hour, we will have traveled 60 kilometers. But if it takes you 2 hours to do those 60 kilometers, your speed would be a lot slower. Another way for velocity is to give the average of the velocity. Now, with the average of the velocity, we know that that is displacement, not the distance. Okay, so a little bit different. So it's the displacement divided by the time. And there's the equation. So that is the initial plus the final, divided by 2 because it is average of 2 factors. Now, when we say that velocity is constant, that means that the speed and the direction are consistent and that the direction is in a straight line. So for example, down here, we have the car that is going in a straight line. This is a good example of constant velocity. Whereas over here, we have a constant speed. You could be going and covering the same amount of distance in a certain amount of time, but because you are going in a different direction at every second while you're going around this circle, you are changing directions, therefore your direction is not constant, your velocity is also not constant. So if speed or direction or both changes, then velocity changes. Acceleration is the rate the velocity changes. It is either the speed or the direction. Doesn't matter. If any of those things change in velocity, then you have acceleration. It can be an increase or it can be a decrease of velocity. So acceleration is the change of velocity, which is the final speed minus the initial speed or velocity, given direction, divided by time. Example, if the driver presses on the gas pedal, or if he or she brakes. These are both examples of acceleration. It is just a change in the velocity. Constant acceleration, you can have a constant acceleration, and this is where you have an increase in the same amount of velocity per unit of time. So for example, at time equals 0 seconds, the velocity is 0. When the object is moving, at 1 second, when you record the velocity, it is at 4 meters per second. At the second at the second unit of time, t equals 2 seconds, we have a velocity of 8 meters per second, which means that your unit of increase in velocity is 4 meters per second. Let's check to see if this is uniform. At 3 seconds, we should have an increase again of 4 meters per second. 8 to 12 is 4 meters per second. At 4 seconds, we have an increase of again 4. So this is a constant acceleration, which is therefore changing the velocity by a set unit per time. An example of positive acceleration is if we had a car that is going at a velocity of 18.5 meters per second, and after 2.47 seconds, the new velocity is 46.1 meters per second. To calculate its acceleration, you know that the equation is v minus u over t. So let's go ahead and plug this in. The final velocity is 46.1, so you're going to take that, 46.1, minus the initial, which is 18.57, or 18.5 meters per second, divided by the time, and that should give you 11.174, or 11.2 meters per second. That is a positive acceleration because the answer is positive. For negative acceleration, this is going to happen with any decrease in velocity. So if you brake in the car, if there's a decrease due to a collision or an incline, maybe that's slowing down your velocity. So for example, if a car is moving in a straight line, but has a steady decrease each second. So first from 22.4 to 15 meters per second, then from 15 to 9.6 meters per second, then from 9.6 to 0 meters. What is its acceleration? So let's take the equation here, and we have its final velocity, which is 0, and its initial velocity, which was the very first piece of information they gave us, which was 22.4 meters per second. And then we're going to divide that by the total of, well, we know that the first second, and third second. So 3 seconds minus 0, which is pretty much just the difference. It's just 3 seconds. And that would give us a total of negative 7.4667 meters per second, or meters per second squared, which is rounded off when you're taking into account sig figs. That would be 7.5 meters per second squared. All right, so let's talk about the SUVAT equations, or SUVAT, however you want to pronounce them. These are 4 equations of motion when we take into account that acceleration is constant or uniform. So all of these 4 equations came from each other. They're derivations of each other. And notice that in each of them, they might be missing one variable. So you're going to be using these in various instances throughout this unit. You are going to have to learn how to use them. So this first equation is actually rearranged from acceleration, the equation for acceleration. And all they did here was they solved for v and they got this equation. The second is displacement. And this is the s equals u plus v. And remember, this is average. And then the time is on the side there. The third equation is useful when you don't know the time or you don't have the time. They never gave you the time, but you have all of these other variables and you wanted to solve for one of the variables here. For the fourth equation, here's where acceleration equals 0, displacement, and displacement equals velocity times time. Okay, so let's say we have a car that is traveling at 10 meters per second and it accelerates at a rate of 2 meters per second squared. So what is its displacement after 5 seconds? So the first step that you want to do in order to solve a SUVAT question is to draw a simple diagram so that way you can see what you're working with. So when you get finished drawing your little diagram, you're going to see something like this. Okay, so step 2 is to make a list of all the items that you have so that you know what you need to solve for. So here we want to solve for the displacement, but we don't have the final velocity, and that's okay. So what we're going to be doing is we're going to find an equation from the 4 equations that we have that have all of the variables S, U, A, T. So you want to look for an equation that has S, U, A, T, given that we have all the variables except for the V. We do want to solve for this, so you do need to have one variable that you want to solve for. So let's take a look at the equations, and we can see that the one item that has all of the variables that we want is this last one. So let's go ahead and use that. And when we solve, we should get an answer of, after everything else cancels out, a total of 55 meters. Here's another example. A car accelerates from 5 meters per second and reaches a final speed of 15 meters per second in 20 seconds. First, find its average acceleration and then the distance traveled in this time. So this is going to be a 2-step process. So we're just going to start off with a simple diagram. And feel free to go and pause this video, try to do this on your own. So just go ahead and solve for the average acceleration and then restart the video. So your simple diagram will look something like this. And we want to know what the acceleration is. So again, step 2 is to make a list of the variables that you have. And we have everything except for we want to solve for the acceleration. So we're going to disregard the displacement right there. And we're going to be solving for acceleration on this time. So you need to find an equation that you can use that has the variables that you have. So that's U, V, A, T. So here are the equations. Find something there, and it should be the first one. So we're going to go ahead and solve, and there's the equation when you actually put the acceleration all by itself. So you solve for A, and that's your new equation. Go ahead and solve that, and you should get an answer of 0.5 meters per second squared. Now, the next step is to find the distance. Now, technically, you probably want to disregard the answer that you got and use the numbers that they gave you if you can. So then that way, if this answer is incorrect, you still have a chance of possibly getting this problem correct on this part to find the distance or the displacement. So in this case, you're going to look for SUVT. Let's go ahead and see if we have anything here. It is right there. And here is the equation, so let's go ahead and solve. And when you get this, your answer should come out to 200 meters. Okay, so that is all the notes for today. Be ready to use this in class next.